Hello everyone, welcome to lecture 20 of this course. In the previous lecture, we discussed the Curry-Harvard correspondence. Today we will discuss some concepts like strong polymorphic types, the problems like type checking or principal typing problem, type inhabitation problem, and dependent types. So polymorphic types. So let us consider the first function. The untyped version of first function is like this, like lambda x lambda. It takes two inputs x and y and returns the first input. The parameters there are x and y. So when we move on to the typed version, we associate types with these parameters. So now you have an annotation like x has type A, y has type B. So that is a typed version of the first function. So the type of this expression now is A arrow B arrow A. That means x has type A, that is the first argument, y has type B, second argument, and the return type is A. So it will be A arrow B arrow A. Now we observe that, so our first transition was we have moved from untyped lambda term to a typed lambda term. But now when we have done this, it says that we have fixed the type. So look, x has type A and y has type B, and as a result, the type of the function is A arrow B arrow A. So suppose here A was int and B was int, so or B was bool, so int arrow bool arrow int. Now it can work in anything like bool arrow int or thing, or it can be some other types. So how to realize this is the question. So as if then, just like the normal parameters that we have, x and y are normal parameters, we have type parameters. So the type parameters can be instantiated with some types that we whatever we want. So then our first thing in progressing, we are trying to make a transition now for now saying, instead of saying that we have a fixed type, now we are saying we have a variable type. It will working for any types. So that is we introduce type parameters, and as a consequence of that we will get what this function will be, a parameterized function. So the parameters are just like normal parameters. So we have now first point is, this was our lambda term where we had a fixed type A and B. So now we say, look, A and B, instead of that we make parameters. That means they will going to take on something. So they are variables. And now we associate these as lambda A and lambda B. So now the whole expression then comprises of different parameters A and B, because they are assigned as types. X, A is a type and B is a type, and you are assigning these to some other variable. So they are type parameters. Whereas these x and y, they are normal parameters. Now the interesting thing here is, how will we if we look this term and we say how to distinguish between different types of parameters. We have A, B, we have x, y. So there are four parameters A, B, x and y. So we said this is a type parameter or this is the normal parameter. How to do? No, now we have to look into the body of this expression. So this is the body actually. This remains same. This is the body. All the things that we are doing, we are moving from untyped lambda. We have given a typed, and then you have introduced this. These are all annotations. They are on this. The body has not changed. So in the body of this, that means of this function abstraction, these ABs will not appear. The type parameters cannot are here. The type parameters will be instantiated to this normal parameter. X is a variable of type something. Y is a variable of type something. So there they will going to come. So this parameters occurrence is limited to here. This parameter occurrence is limited to here. And in this body, we may have x, we may have y, we may have z, whatever. These are the normal parameters. That is the difference between these two. So now we have move a more generic structure, and this is called polymorphic, because it is going to work not on one particular type A or B, uppercase A and B, rather anything. So if we instantiate, for example, with this A and B, uppercase A, B, by beta reduction, we are going to get back this one. So this is what then the transformation, then we have moved from untyped to typed and then parameterized type. That is the polymorphic type. So the parameterized first function is represented in this way. Now in order to distinguish, that is what we are discussing, that by looking at it, if you want to say look, these parameters are different, so we write, instead of normal lambda, we write big lambda, and big lambda we are going to use as a binding for the type parameters. So there are two type parameters here, so the bindings are done by big lambda, and these are normal parameters, and this is how the structure will look like. Parameterized type function will look like this, and the generic form will be lambda a dot m. So we will give the language of m, and then we will see this how these multiple occurrences are coming. Big lambda a dot m. A is a type variable. So now when we have this sort of a term like lambda a dot m, the type is for all a dot type, that is a universally quantified types. So if you recall TA lambda, the language is called weak polymorphic because we are not having these universal quantified types. Now when we introduce this, the type that we need to have is for all a dot type, that is universally quantified, meaning that for all a, the body of m has type tau. So for example, this first function, the type will be for all a for all b, it will be a arrow b arrow a. Now we look at some more types, like second is like first, it will be instead of the first argument we are returning the second argument. So the parametric version will be as before, and only the term body is now changed to y, and the type then would be instead of a arrow b arrow a, it will be a arrow b arrow b, and we have quantifiers for all a for all b. Next we take on the apply, another function we discussed is, that means you are applying a function, that means lambda x lambda y x y. X is a function type function and y is simply a variable here. So the parameterized type will be lambda a lambda b. Now you see the interesting thing here is x is a or b, it is not x is a. X is a function type, hence this must be a or b, it cannot be a. A cannot be applied to b or a, it has to be function type, so it is a arrow b, and y is a, otherwise application will not go through, arrow e will be violated, and hence we note very carefully that it is a arrow b a, and the body is xy. So the type of the parameterized apply is for all a for all b, a arrow b arrow a. A arrow b is a function type. This bracket is important. This bracket is important because if you recall, it is called the secondary arrow. This is the structure. There are two parameters, so there will be two things. There are two parameters or two arrows will be there. This is internal thing. This is a function type. This is different from normal type. So we have a arrow e. So it says that there is a function. It takes as input a function, another normal thing, and it gives b. That's the idea. Now we have also seen polymorphic types appearing in Haskell in different ways. That means the polymorphic function is one that works for all types. So in Haskell we have seen the length of a list. The length function is independent of the type of the elements of the list. So if list A denotes a list of type A, where A is a type variable, in Haskell we write it as A is a type variable, the length function works for a list of any type. So the type of the this length may be written as a universally quantified type as for all a, list a arrow int. Now suppose we have written like for all a arrow int. We may from our natural way of writing, we may just write a arrow int. So we may say then what is wrong with this? So that means if I can write then if a is int, so it will be int arrow int. Then the length arrow takes an integer and it is telling the length of this integer is something or whatever like that. Like that we will also get. We have a string, then we are saying length of the string is this. It is not that intended. We are not writing that 235 length is 3. This is not we are saying. So that is why in an informal way we have written it is a list of type A. That means the list whose elements are of type A. If that be the case, then it is going to return a type integer. This is why. So this is wrong. So we will not write this. So this is the correct way of writing this, although it is informally we are writing. And we are seeing other functions also like head, like tail, then reverse, and there are several other operations on list that they are all polymorphic. We now discuss the type languages. First we consider the language that was used in TL lambda, that we named it L2, and that is weak polymorphic in that sense that for all quantifier is not used. Universally quantified types we cannot do it in TL lambda. So here the syntax is that first is A is a type variable, and if A is a type, any type variable is a type, and if sigma and tau they are types, then sigma or tau is also a type. This is that simple and that is called simply typed lambda calculus. This is what when we are saying that lambda terms together with the language of types is coming from this grammar, and then that is what is TL lambda is all about. And we can have examples of these types. It will be A arrow A. So we can generate A arrow B and A arrow B and A. So we combine them with this arrow. So we get this. Similarly, we can generate A arrow B and we can generate B arrow C. You can combine them, get this. Then we generate A arrow C, arrow A, and likely from this grammar C. So these are some examples of this language. Then we move on to a strong polymorphic. That means this language is enhanced with a type for all A dot sigma. That means this part is the language of TL lambda. Now we are introducing for all A dot sigma, that makes it strong polymorphic. That means a universally quantified type. So this is the language called system F style or L3 that we have named, and the following notations we are going to use from the paper named Type Systems by Luca Cardelli. So the examples of the types, some of them would be, so that is for example the identity function. So we are saying for all types A, the identity function type is A arrow A. Now this is the first function. So for all A, for all B, the type is A arrow B arrow. So here you see in this, when you move from one quantifier to two quantifier, likewise we can have several quantifiers. So one type of formulas that we can obtain from this grammar is that the quantifiers appear as prefix of a type. So this is the type and all the quantifiers will come before this. This is one kind of formula that we can obtain from the grammar. Now from that grammar we can also obtain these types of formulas we can also generate. So now the quantifiers can be more deeply positioned in a type. That is, it is not that all of them are coming before and then the type. All quantifiers followed by type. It is not a for all A, then for all B, then they have a nesting of many such. We can have arrows here, lot many, and then again there may be for all quantifier. So this makes the language very expressive. Now then we will look at this language now in detail. So now recall that when we studied lambda terms, that means the pure untyped lambdas or lambda calculus, that language that we obtained, and pure lambda terms. So this was generated in this way. X is a variable, this is an abstraction, and this is application. Now when we moved on to type, that means in system F style that we are writing, so now we have certain new things. So this is abstraction as before, this is variable as before. Now we are saying X has type annotation in this abstraction, the type annotation in this abstraction is sigma, and sigma is coming from this language. This is this language, type language. So you can have different whatever sentences of this sigma, we are going to give it as a type. Now the important things here are these two things. So this is called polymorphic abstraction. Lambda, a big lambda A dot M is called polymorphic abstraction. And we have seen that means we have now type parameters. This language that we had discussed informally, that is a type parameter here. A is a type parameter. Now this is an abstraction, but this is a type polymorphic abstraction. That means for all now we are saying types variables, type parameters we have, and then we are doing this abstraction on this. That means this will now give by this grammar lambda A dot M. Now I will use it and I will again write lambda A dot M. That means lambda B dot M, A we can replace by B. So we can have again like our first that formula, we can have lambda A, lambda B dot, then we can have this lambda M. This X part we can have, substitute this So we can have multiple quantifiers in this way. And now once we have this type abstraction, polymorphic abstraction, we need to instantiate it. That means we want to now apply some types onto this expression, so that now these things will get these types of things we are going to get. This form we are going to get. So we do this m sigma. M now applied to sigma. Sigma is a type here. So you see that very carefully that A is a type variable here. Sigma is this type language and this will be a type. Sigma is a type, A is a type variable. This is called system F2 in this type systems paper. It is written F2 because they discussed a first order type system. So that is why they named it F2, because first order type system, what they had was, instead of this A, they had basic. Say they associated there was a basic and they had this sort of a thing. K belongs to basic and this was this. It was not there. Then that is why they made it second order type system. So we will say system F style, and it is system F style, it is named like this, and it is actually second order polymorphic type lambda calculus. Second order means we are moving up for all quantifiers. This sort of structure, when we move on from this to this, it is called second order polymorphic, and it is polymorphic because of this one, polymorphic abstraction. So either way we can call it system F, or we can call second order polymorphic type lambda. Okay, now we discuss two problems. One is the type checking problem, another is a type inhabitation problem for different languages. Now it is important to note that we are adopting Curry style and not chart style, since in chart style there is no such thing as non-typeable. So recall that in chart style the non-typeable terms are considered meaningless, so they are not considered. So all the things that are in chart style, they are all typeable. So then there are question of whether a term is typeable or non-typeable does not arise in chart style. So then all our discussions that we are going to do is based on Curry style, that is followed. The language, that means we are taking arbitrary lambda terms and we are asking some questions related to that. So the first problem is called the type checking or principal typing problem. That is, so it is given a lambda term whether it is typeable. That means, this means that does there exist a tau for m. This is what the meaning of type checking or principal typing problem. Now if the answer is yes, it will give a principal type for m. Now if we are in the system TA lambda, the principal type algorithm we have studied, it will give the, it will decide. That means it will give either yes or no. So if it is typeable, it will give the principal type as well as the principal deduction. And if it is not, then it will give a correct statement that it is not typeable. So we have seen this algorithm, principal type algorithm. So that means for TA lambda, this problem is decidable. Now we say, now m and tau are both given. Now we are asking whether m has type tau. So in order to solve this, we can first apply principal type algorithm on m. So we will, if it is typeable, then it will return the principal type. Then we will check whether this tau is a substitution instance of the one, could be it is identical with tau. This tau is identical with the principal type, or it is a substitution instance. That is doable, that we can easily do. So that means this problem is decidable for TA lambda. So that means these two problems, the first problem and the second problem, they are more or less similar. Now we look at the type inhabitation problem. Now type inhabitation problem says that we are given a type tau and we are asking whether there is a lambda term that has type tau. That means tau, can tau be assigned to some lambda term or not? That is the question that we are asking here. Now as we discussed in the previous lecture, that is the Curry-Harvard correspondence. This is where Curry-Harvard correspondence comes in. That means if we are in the system TA lambda, we cannot answer this question. So what we did, we transformed or interpreted these types as a logical formula, and now the tau we are now looking at is a logical formula, and in that IIL, now that the type language for TA lambda is the same as the language IIL. So now we ask a question whether tau is provable or not in IIL. Now if that be the case, if we know that the probability in IIL is decidable, then all we have to now do, take the proof and do that syntactic transformation and get M. And if it is not if it is not provable, then we say there is no M. So anyway this answer can be given, and this IIL, for IIL it is known to be decidable. So please we refer to Hermann Goebbels, a very nice discussion, and in his lecture notes he has written Introduction to Type Theory. There a detailed discussion is given in this regard. So we are referring to this paper. Now we are moving on to some more expressive systems. The language is very expressive now, that is system F style. It is strong polymorphic. Now for both the problems that we have, TCP and its variant and TIP, they become undecidable. So what is happening here, when the language has become very expressive, both these problems now will become, as now it is known that this will be undecidable. So for system F, this problem is known to be undecidable. This was shown by Wells in the seminal paper on typability and type checking in the second order lambda calculus are equivalent and undecidable. It appeared in Leaks 1994. So we refer to this original paper for this result. We are merely stating that it is undecidable. Now the other problem, type inhabitation problem, the logic in system F style is second order intuitionistic implicational logic, and provability in this logic is known to be undecidable, and hence this problem is undecidable. Again, there is a detailed discussion given in Goebbels in that paper, Introduction to Type Theory. So we refer to that paper. You are requested to please look at this paper. Now that we have seen that when we move to a system F style, the language is very expressive and the problems become undecidable. So we may think of that, if you recall that in that language, that quantifiers might appear at both arbitrary places or they may appear as a prefix, that all the quantifiers appear before a type. So in that language, if we give a restriction that look, we are going to only consider these types of types, that means we have a type and it is all prefixed with the quantifiers appear before the type, where sigma is our TL lambda language. If that be the case, now we are getting decidability. Both the problems again become decidable. Now the PT algorithm that we have studied, principal type algorithm, can be extended to incorporate types having this form. And this logic that we have now, that is of intuitionistic implication logic, is a very weak extension of IIL. So that makes it decidable. So again, we refer to this paper, it's a very nice discussion given there. So then these intermediate points allows us the practical type systems in Haskell, for instance. This is what is going on. The type system is built on this concept that when we write a type signature in Haskell, the universal quantifiers may be omitted and all type variables are implicitly universally quantified. That means when we are writing ID signature, type signature of ID is AROA, it is like saying for all types A, this function has AROA. This is the core aspect of Haskell's parametric polymorphism. That means this is implicitly equivalent to saying ID, signature of ID is for all A, arrow A. This is the idea that translates. So now the language is in between system F and the language of TL lambda, and that's this results in a practical type system, and that is we are addressing now polymorphism in an implicit manner, and then these things we are going to get, and we have a language, functional programming language, where we can address these things. And so these two problems that we had, that restrictions resulted in a practical type system in Haskell. Okay, now we discuss dependent types. So dependent types, this discussion is based on a paper named Dependent Types at Work, 2009, by Anna and Peter DBR. Dependent types are types whose definition can depend on the value of a term, not just its type. So earlier things that we have seen. Now we are moving to this one. This is a quite a different paradigm, but it is useful. For example, in proof assistance, this is used. So the idea is, suppose we want to say that we want to work with vectors of length n, and the vectors elements are from some type A. So suppose we want to say integer. So we have a vector of integers of length n, say vectors of integers of length 3. So we say type an of vectors of length n with elements of type A. Now the type depends on a value. Earlier we were not saying anything like value. We are saying it is a type integer, type bool, like that, but it is not a value. So if I change it, I say change vectors of length 5, that itself is on one type. Vector of length 3 is another type. Now this makes it quite a different notion that we are now seeing here. Now this encodes extra information like length into the type, ensuring stronger correctness guarantees. Now the type system, in some applications we might need certain things like this, not working on arbitrary vectors, but some vectors of length 3 say. So we will not consider vectors of length 4 or 2, it should be of length 3. So this is the idea that is given on dependent types. That dependent means, in the sense, it is depending on a value of a term. Earlier there was no notion like value of a term, it was like types. Now this type a to the power of n, we can give an inductive definition. So we can say a to the power of 0 is some one unity, we can write in that language form. A to the power of n plus 1 recursively, that we are writing a times a to the power of n. This is the, so this another nice thing with independent types is that dependent types is that we can give an inductive definition with it. So likewise, instead of saying vectors, we can have a general thing like matrix. So we can have a type a to the power of n, n cross m. That means we can say we are going to work with vectors of always matrices of sides, square matrix of 3 by 3 or 4 by 4. Other types of matrices we are not considering. That might be having some interesting applications. So these are the things that are classified as dependent types. Now for example, we have been working with lists, and in Haskell we have seen lists in action in different examples. So suppose we write, this is a notation to say that this is a list of type A. Now is it a dependent type? Now here it is not depending on a value. It is saying it is a list of type A, means it could be a list of integers, or a list of strings, or list of booleans. It is not depending on anything, so it is not a dependent type. So if we want to make it a dependent type, then we have to say this is some notation that list A n sort of a thing. That means it is a now dependent. That means we are saying list of size 3 or list of size 10. That would make it a dependent type in this terminology. Then we have different data structures we can take up on, and we say a binary tree of height n. So we are going to consider not arbitrary binary trees, but some fixed n. Say n is of depth 3. The depth height 3 binary trees we are going to work with, and this might also lead us to other data structure like balanced binary trees, height balanced. We may say that no two subtrees will differ by some length, and that sort of things can be done. So we are working not on binary trees, binary tree of integers or binary trees of real numbers, but we are saying now binary trees of some type but having height something. So height now is a dependent type. This makes it a dependent type. Now, however, this dependent type is not that it is not that we are not familiar with actually. So it is there. It is a common practice in Fortran. It was there. It is there, and in C-like declaration, if we say we are declaring an array. So this says int array size 100. That means it is not just saying that an array of integers. It is saying an array of integers of size 100. That means we have specified, we have declared that it is of size 100. That means it is a dependent type. So it is there in practice in some languages, but it is more common to use it in other proof, when we are trying to give automatically giving proofs, there this usage is important. So another example would be a finite set of size n. So is a set fin n that contains exactly n elements. So if you have say 4, so this might contain the elements like 0. So we might have a 0 representation for 0, we may have some notation for 0. I have just used 0, it will be suck of 0, successor of 0, and then is successor of 0, and so on. So this will be a finite set of size n, not arbitrary sets but a finite size. So the applications that are there of dependent types is a proof assistant helps in helping a human with a proof. So Coq is a proof assistant, and the type system of Coq supports dependent types. And Agda language is what is used in that paper, in the dependent types paper, and using that they have defined these functions, dependent types, and it is a dependently typed functional programming language. Haskell is not a dependently typed functional programming language, and STLs is simply typed lambda calculus, and the system F that we have seen, they do not support dependent types. So with this we end the discussion on dependent types, and if you are interested, please look at this paper, and if you are interested to do research in this area, this might be very helpful. It is a very strong connections from Martin-Löf type theory. All these things are descendants of Martin-Löf type theory, and if you want to look at advanced topics on type theory, so please take a look at this paper and other additional references given in the dependent types paper. So to summarize that today's discussion, we discussed strongly polymorphic types and these different problems like type checking or principal typing problem and the type inhabitation problem, and we have given a very brief exposition on dependent types. And these are the articles you are requested to see. So first one, we are already familiar with this paper by Cardelli, type systems, and we have also used this paper, Introduction to Type Theory by Hermann Guevars, and for that particular result on undecidability you can see Wells, and this is that dependent types work by Bow and DBR. So today we have completed this course on introduction to lambda calculus, and now we will summarize what are the topics that we have covered in this course. So in the first 10 lectures we discussed lambda calculus, and the other from 11 to 20 other lectures we considered typed lambda calculus. So in untyped lambda calculus we discussed topics like lambda abstraction, then lambda application, then we discussed currying, then we discussed beta reduction, alpha renaming, eta reduction. Then we went on to discuss normalization, different normal forms like call by name and call by value. Then we discussed Church-Rosser theorem. Then we studied how to encode different data structures and operations. Like first we studied conditionals like if then else, how to encode in lambda calculus. Then recursion, for that we introduced Y combinator and discussed the properties like fixed point combinator. What is a fixed point combinator? And then we discussed how Boolean functions can be encoded in pure lambda calculus. We also discussed charge numerals and then operations like successor function and then other arithmetic operations, arithmetic, multiply, etc. And we also discussed how to design simple functions like is0 successor function, and how these concepts we can use to do for addition, multiplication, and so on. And we also touched upon other combinators like Z combinator, Turing combinator, and then we discussed SKI combinators and how to simplify them using some rules that we had. We also discussed restricted lambda terms like BCK lambda term, BCI lambda term. And then we showed how some data structures like pairs and list can be obtained in this pure lambda calculus. And the predecessor function also can be constructed using pairs. So, and thereafter also we discussed a practical functional programming language Haskell, and we showed how certain concepts given in pure lambda calculus, they are translated in Haskell, and how certain operations that are there in Haskell and certain functions are embedded, and the computations in Haskell and lambda calculus, how they, what is the similarity between these two. These things we touched upon these topics. Then when we moved to typed lambda calculus, we gave an introduction of types and meaning of the type systems and the properties, different properties, and then they were formalized, like we gave a construction tree of a type of a term and the theorems associated with it. Then we developed type system, simply typed lambda calculus for the language simply typed lambda calculus. We gave a system called TA lambda, and there we showed how the deductions can be done. And then we moved on to addressing the principal type of a term, and we discussed the principal type algorithm and the related concepts needed to discuss the algorithm, like unification, most general unifiers, substitutions. And thereafter we studied the Curry-Harvard isomorphism or the Curry-Harvard correspondence, and for that we studied intuitionistic implicational logic. And today we have studied strong polymorphic types and the different problems like type inhabitation problem and the type checking problem and their decidability issues for different languages. And then we gave a very brief exposition of dependent types. So this was all about this course. We thank you very much for your kind attention, and I hope you have enjoyed this course as much as I have enjoyed delivering these lectures. Thank you very much for your kind attention.